Okay. Hola a todos y gracias por inventing papas arrugadas. So, my name is Milica. I'm Vivid Digital on Twitter. I'm a contractor for Google. I work on web.dev, where I write about performance and developer tools. So if you, for example, have long load times or poor application responsiveness, web.dev is a website where you can learn how to fix those things. And if performance is something you care about, and I really think you all should, definitely come talk to me after this talk. I'm also a Mozilla tech speaker, and I interned at Mozilla on a browser engine called Servo. Parts of Servo are what makes Firefox fast today. Servo is fast because it was written in Rust, and it can do a lot of things in parallel. Now, Rust is this cool new systems programming language, kind of like C or C++, but without the issues with memory safety. So I got to learn a little bit of Rust a while back, and I really liked it, but I'm a web developer, and I really love the web, and I didn't want to move away from it. This was in 2017, when support for WebAssembly had just landed in the browsers, and being at Mozilla at the time, it was the perfect opportunity to learn more about it. In short, WebAssembly is a way to run code that's not JavaScript in the browsers. So today, I want to talk to you about how we got to this point and why do we actually need WebAssembly. I'll explain how it's different from JavaScript and what does it realistically mean for the future of web development. Chances are you actually came across WebAssembly in the wild already without even knowing it. I'll show you some practical examples and some fun ones, so let's get started. In every browser, whether you use Chrome, Firefox, or Safari, code is interpreted and executed by a JavaScript engine, which until recently used to only run JavaScript. But what about C, C++, or Rust? JavaScript is just not ideal for every task that we want to perform. That's where WebAssembly steps in. You do not write WebAssembly. You compile other, higher-level languages to it. But why would you want to do that? Why do we need WebAssembly? So the short answer is performance. And there are really many cases where performance is really important, but I want to focus on one specific for start. And that's video games. Now, some of the very first WebAssembly demos were video games. In 2017, Unity Engine ported Tanks to the browser. And then last year, someone ported Doom 3 to the browser. And also in 2017, Epic made this demo of their Unreal Engine 4, which is the Zen Garden. This is a GIF, so it's a bit choppy. But if you open this in the browser, it runs really well. Now, what's happening here requires a lot of mathematics and careful memory management. Now, there are falling leaves, fluttering butterflies. To render this on screen, the browser, any engine, has to implement physics, and it has to calculate the positions of millions of pixels in each frame. Now, video games in general often definitely have to implement audio, and they often implement artificial intelligence too. Now, these are all really performance-intensive tasks where JavaScript is just not good enough. This is a screenshot of the first website ever that Tim Berners-Lee published about 30 years ago. JavaScript was invented at that time to bring some interactivity to the web that was full of hyperlinks. It was designed to be easy to learn and easy to write. But it wasn't designed to be fast. Now, over the years, browser added improvements into the way they optimized JavaScript. As it got faster, we got many applications that were previously desktop-only coming to the web. Gmail is a perfect example of this. It came out in 2008 when Chrome came out with its very optimized V8 engine. Now, today, you easily edit documents or send emails from the browser, but there are still areas where JavaScript performance is a struggle. Video games were an early goal for WebAssembly, not because we all wanted just to play video games on the web, but because enabling this performance-intensive use case would open the web to many more other applications. Now, if you for a second think about cases that are not video games, where you use desktop apps. It could be video editing, or maybe music production. And there are many more cases where WebAssembly could help, like 3D rendering, virtual reality, CAD applications, VPNs, remote desktops, and the list goes on and on. But why would you want all of this on the web? What makes the web so attractive? To me, the beauty of the web is that it's kind of like magic. It just works anywhere. There's no download, there's no installation, and it has safety built in. Browsers have this thing called sandbox, which keeps code running in the sandbox from messing with your system. Now, when you visit the site, you never think twice before clicking a link. But none of you would just download a random binary and execute it on your computer. And my favorite thing, sharing on the web is as easy as it gets. Links are just clickable strings that you can put anywhere. And we all know that's not how app stores work. So web is definitely a universal platform which makes your application available on practically any device. Nowadays, even refrigerators come with browsers. And for us developers, this also means it's easy to maintain a code base, and it makes the updates simple. Now, because of all of these things, web came from a small place with a simple scripting language to this huge platform filled with powerful applications. But really, it was still fundamentally powered by a scripting language that was not designed for all of this in the first place. So what does WebAssembly actually bring to the table? I'm going to focus on three things. That's speed, portability, and flexibility. Let's talk about speed for starters. WebAssembly is a low-level binary format. This is what it looks like. It also has a textual format that you can use for debugging. You could also write it by hand if you're really adventurous, but that's not really what it's meant for. The binary format is what's delivered to the browser. Now, binaries in general are much smaller than textual JavaScript files. This makes them faster to download, which is especially important on slow networks. And JavaScript's textual format means that the browser has to parse it. And parsing is actually not a simple operation. It involves lexing, tokenizing, turning that into abstract syntax tree, and then turning that into binary. Now, remember how WebAssembly is a binary format? That means that there's no parsing, just decoding, which happens much faster. Another difference between JavaScript and WebAssembly is the type system. JavaScript is dynamically typed. When you write x+1, you don't really have to specify what x is. So it could be a number, a string, a boolean, and you don't even compile that code. You just give it to the browser to figure it out. So this makes it fast to write, but it means that the browser has to do a lot more work. It has to optimize your code, and to do that, it has to speculate about types that you're using. If the browser makes a wrong speculation, then it has to re-optimize the code as it's running. Now, WebAssembly, on the other hand, is statically typed. So the engine doesn't have to do that speculation in optimization. And most of the optimization in the first place happens when you compile from the source code, from C or Rust. And another thing that gives WebAssembly a speed boost is streaming compilation. So kind of the same like you watch a YouTube video as it's being downloaded, the same way browser can compile WebAssembly binary as it's downloading it. So for a small binary, this practically means by the time the download finishes, the code is ready to run. All of this makes WebAssembly fast, but it's not like JavaScript cannot be fast. We can write fast JavaScript today. The problem with that is in order to write fast JavaScript, you have to write it in a really special way that works with the browser's engine optimizations. And the problem with that is that these optimizations are not the same in every browser. So if you optimize your code for some quirk that V8 does to speed up your code, it actually might run slowly in Firefox's SpiderMonkey. And another problem, these optimizations change over time. So if you wrote fast code for Chrome last year, next year it might not be as fast because they changed that optimization. WebAssembly, on the other hand, gives you reliable performance, and that's what makes it so attractive. The next thing is portability. How do you take things from one place to the other and have it just work? Portability was one of the main goals in designing WebAssembly, so I'm going to go over that design really quickly. Just so we're all on the same page. Assembly typically refers to humanly readable languages that are similar to machine code. Machine code is what your processor understands, a bunch of numbers. Now, every high-level programming language gets translated down to machine code in order to run on the processor. And different kinds of processor architectures have different machine codes and different assembly for each of them. Now that you know the exact definition of WebAssembly, and if you have been paying attention, it's obvious that WebAssembly is not actually an assembly language. That's because it's not meant for any specific machine. When you write code to run in the browser, you have no idea which machines it's going to run on. So WebAssembly is actually an assembly language for a conceptual machine. That's the least common denominator of popular real-world hardware. When the browser downloads WebAssembly binary, it can quickly turn it into any machine's assembly. Now, to run an application on a device, it has to be compatible with the device's processor architecture and its operating system. In reality, this means that you have to compile your code for every combination of processor architecture and operating system that you want to support. Now, that's a lot of work. But with WebAssembly, there's only one compilation step, and your app works in every modern browser. Now, this enables two really good use cases. First one is porting legacy applications to work on the web, and the other one is just building applications in a single code base that can work across platforms. C++ is a really good language for this use case because it's supported practically everywhere, including iOS and Android. Now, another really exciting thing about WebAssembly is its flexibility. Until now, JavaScript has been the only fully supported language on the web. But today, with WebAssembly, us developers can choose other languages to work on the web. And even more interesting, people who previously couldn't be web developers because they didn't know JavaScript can actually now come and write applications to the web. I think this diversity of perspectives will make the web a more interesting place. And another technical aspect of WebAssembly's flexibility is how it fits into apps. So WebAssembly compiles into modules that you can use inside your web application, and they can communicate with JavaScript modules. So WebAssembly is not a replacement for JavaScript. It can work alongside JavaScript. And JavaScript is really good at a lot of things, actually. New frameworks are very efficient at DOM manipulation. And sticking to pure JavaScript is probably going to be both faster and easier for a lot of you. But because they work together, you can now use WebAssembly for some specific things, like write a core functionality that needs high performance in WebAssembly, and the rest of your app write in JavaScript. Or if you have a performance bottleneck today in your apps that you just couldn't solve with JavaScript, now you can switch to some other language that's maybe better suited to that problem and compile it to WebAssembly. So this really comes down to using the right tool for the job. Fully supported languages today are C, C++, and Rust, but the list of languages that are working on support is really big. So .NET, Kotlin, and Go have already shipped pretty decent support. .NET has this framework Blazor that's scheduled to have the first official release in 2020. And there's even a framework for making a front end for apps in Ruby. It's called Prism. So if any language you're interested in, just Google WebAssembly support, and you'll definitely find people who are working on it. Now, one language that's really interesting to me as a web developer is TypeScript. AssemblyScript is a compiler that can take your TypeScript apps and compile them to WebAssembly. Now, it can't be just any TypeScript. It has to be strictly typed, but still. I think this is awesome, because as a web developer, even though I know a bit of Rust, I'm still way more proficient in JavaScript. And I definitely do not expect other web developers to just drop what they were doing and go learn C or Rust. But as JavaScript developers, TypeScript is something that most of us are familiar with, and even if not, it's something that you can pick up easily. And this gives you the opportunity to try WebAssembly without learning a whole new language. Moving on to how this actually works. You need a tool to compile your programs into WebAssembly. Compilation step is something that us JavaScripters didn't have to bother with for a long time, but now with Webpack and Babel, that's not so true anymore. So in WebAssembly world, for compiling C and C++, there's a compiler called Emscripten. For Rust, its own compiler, Rust-C, can output WebAssembly directly. And WasmPack is a tool that can package your modules for publishing. Now, on the example of C and Emscripten, this is how that would work. Emscripten takes your source code and compiles it to WebAssembly. But it doesn't give you just a WebAssembly module. It also gives you an HTML file and a JavaScript file. Now, you need these things because WebAssembly, unfortunately, doesn't have direct access to DOM API, to web APIs such as DOM or WebGL or pretty much anything. Now, to work with any of these, even to display the output of your program on a web page, WebAssembly has to go through JavaScript. So Emscripten will generate this boilerplate code in a JavaScript file, and then in HTML file, you load this JavaScript bundle and output your program in a text area or a canvas element. Now, this sounds like a bit of a hassle, and in Rust world, there's a tool called WasmBindGen that can make most of this stuff pretty easy and seamless for you, but still, it's not the smoothest process just yet. And there are a couple more tricky things. WebAssembly only has 4 types, and they're all numbers. So if you want to work with more complex objects, even a string, for example, you have to encode it into an array of numbers and then pass a pointer to it. It also doesn't have direct access to JavaScript variables. So all these things will change pretty soon. There are proposals like reference types and WebIDL that will make working with WebAssembly and JavaScript communication pretty easy. But today, that's just not there yet. So for now, good advice is just to use WebAssembly to offload big chunks of work. Some resource-intensive tasks, like maybe image resizing or processing an audio stream, something that gives you a direct output. Now, I guess you're wondering, are people actually using this in production today? And the answer is yes. Now, let's see some examples. One of the use cases I mentioned are open source libraries. So libraries written in other languages ported to the web. If you've ever tried to upload a huge raw image to Facebook, it actually went through WebAssembly code, because Facebook is using this really old library called libjpeg. I think it's over 40 years old. It was written in C and just compiled to WebAssembly, and now it's used to compress your images. And if you ever play an audio file on Wikipedia, they're also using a C library called Opus that decodes your audio files. And in computer vision, there's this library called OpenCV. A part of OpenCV that deals with face detection has been compiled to WebAssembly and ported to the web. Now, this actually enabled to use a really well-tested open source library for face detection on the web and achieve performance that's an order of magnitude faster than any other available JavaScript solution. And the use case that's probably the most interesting to JavaScript developers here is writing hybrid apps, where only parts are in WebAssembly. Squish is an apple from the Google team that deals with compressing images. So it supports several compression algorithms like MozJPEG or WebP. Now, All of these algorithms have been written in different languages, mostly in C++ and compiled to WebAssembly. But other parts of this app are written in other languages. The resizing function is written in Rust. And the function for rotating the image is written in assembly script compiled to WebAssembly. And the user interface of this application is written in Preact. The app is really fast. And if you visit squish.app, you can even try it on your mobile phones today. And some big apps are using WebAssembly too. Figma is a tool that allows designers to collaborate and share their files easily in the browser. It's mostly written in C++. It has a really powerful 2D rendering engine that's written in WebGL, and it can handle really large documents. But Figma's user interface is written in TypeScript and React. And I also mentioned you could port legacy applications to the web. One really cool example is AutoCAD. This is an engineering software used for making, I don't know, electrical circuit plans or floor designs. It's written in C++. It's been around for maybe 35 years, which is older than the web itself. And in 2017, they were able to port it to WebAssembly and bring it to the web. So this allowed them to use their application that's over 30 years old without having to rewrite such a huge code base and just make it available on the web. And another legacy application is Google Earth. It came out 14 years ago. Google Earth allows you to zoom in on your childhood home or stroll the streets from across the world. But when it came out, in order to do any of that, you had to download it and install it on your computer. And the reason for that is the kind of performance that is necessary for rendering the entire world in real time was just not available on the web. But this year, it was ported to WebAssembly, and it's available on the web. And there are many other examples. Like, people are doing weird stuff. Someone ported Windows 2000 to the web with WebAssembly. So now we have an operating system running in the browser. And yes, you can totally play pinball in it. And another fun example is WasmBoy. This is a Game Boy Color emulator, which was compiled to WebAssembly using assembly script. And it comes with an interactive debugger, which was written in Preact. And many other examples are there. eBay is using WebAssembly in their web application for barcode scanner. Ethereum cryptocurrency implements their virtual machine in WebAssembly. Then Iodide is this scientific visualization tool available in the browser. Recently, someone made a Flash emulator called Ruffle. And PSPDF Kit is this framework for working with PDF files in the browser. There's an online gaming platform called DigiPlay, and many, many other examples. And WebAssembly is actually supported in all major browsers. Its support is over 87% for all of the global users. And this is really different from how things were in the past. Some of you might remember these images, and the younger crowd here probably never even seen them. So these are Flash and Java applets. And the reason why we don't see them today anymore is because they're dead. So yes, they were pushed by competing companies, and they were never really a part of web platform. They all worked as plugins. And there was never a standard for any of them. So they just kind of died out. But WebAssembly, on the other hand, is part of the web platform standards. So there is a committee. All of the major browsers are working together on implementing new features. And I think this is the reason that it will stay part of the web. Now, as a fallback for older browser, there's this thing called ASM.js, which is a subset of JavaScript that works only with numbers. So you can compile your C programs to ASM.js to support older browsers like Internet Explorer, for example. ASM.js is actually the way how WebAssembly came into being. It was its predecessor. So the important thing. What are the benefits for JavaScript developers here today? I think the integration of WebAssembly with JavaScript will actually make JavaScript ecosystem stronger because it will allow us to use all the best libraries from all the other languages. And I think a reason why JavaScript succeeded so much in the first place is NPM and ease of distributing modules and using other people's code. Well, WebAssembly modules are actually also available through NPM. There's over 600 of them today, and I think the trend is only going upwards. So what if you really don't think you're going to use any of this? Absolutely no intention to make a video game, the next Photoshop, or anything more intensive. Do you get anything out of WebAssembly still? Well, yes, you can get benefit through improved tools and improved frameworks. These things are already happening. Firefox DevTools and Webpack both use a source maps library, which was initially written in JavaScript, but then recently rewritten in Rust, compiled to WebAssembly, which made it 11 times faster. And this is something that we are all using today. And as for the frameworks, Ember investigated implementing its virtual machine in Rust. React is not really doing the same thing, but there's really room for improvement there, because React's DOM-diffing algorithm is something that could be easily parallelized. And Rust is a perfect language to do such thing. And if you compile it to WebAssembly, you could just get those benefits today. So what else is there? What else can WebAssembly do? Well, it has actually started expanding beyond the web. Now, WebAssembly initially ran inside browsers, but because it's an assembly language for a conceptual machine, it actually means that you can make other runtimes that can run WebAssembly and work on different operating systems. And this is something that's already happening. Serverless providers like Fastly and Cloudflare have made their own runtimes that allow you to run WebAssembly in the cloud. So before this, most of serverless providers enabled you to use JavaScript or Python. But now you could technically use any language and get the same benefits on the web, which are, in my opinion, I think the pay-as-you-go model and the automatic scaling, but now in pretty much any language. And also there is Wasmer, which is a universal runtime that supports WebAssembly, and many other are popping up. So this WebAssembly thing obviously works. But what else is there? OK, let's see what lies ahead. Browsers are already working on new features. The support for threading is already in Chrome Canary. I think in Chrome Canary, it used to be behind Origin trial. And in Firefox, threads were implemented, but then had to be turned off because of Spectre and Meltdown bugs. But I think they're working on enabling it real soon. And another really important thing that's coming to WebAssembly is garbage collection. This will enable support for languages like Java or C# to be much easier in WebAssembly. And another really important thing are better debugging tools. All the browsers are working on them, something that will allow you to have your WebAssembly module and easily inspect the original source code written in C or Rust. Just yesterday, Chrome DevTools announced that they are supporting the dwarf debugging format. So today, you can debug C, C++, or Rust in Chrome DevTools. And another really cool thing, soon enough, you could import your WebAssembly modules in your app just using a script tag. So if all of this sounds interesting to any of you, how about you just try it out? If you want to poke around without committing to dealing with all the tool chains, there are a couple of web-based IDEs that can work with WebAssembly. One of them is WebAssembly Studio. It gives you Hello World projects that you can try using, or you can write something on your own. And another interesting thing is WebAssembly Code Explorer, which allows you to poke around the binary file format or the textual file format of WebAssembly programs. So this is Canarias.js. I really want to say I think JavaScript is a great language. It's flexible enough to do almost anything with it. And I think it will still have its place in web development. It's not going anywhere. WebAssembly will just fill in the gaps that JavaScript couldn't. So WebAssembly is really not the end of JavaScript. I think it's a new beginning for the web. And if you want to learn more about any of this, check out Code Cartoons by Lynn Clark. And if you have any questions whatsoever, you can ask now or come see me later. I really love to meet all of you. So, gracias. Questions, anyone? Go ahead.
Hi, thanks for the talk. It was great. You spoke about compiling like big apps over to WebAssembly, and I was just wondering whether there's any support for like breaking down apps into modules so that it'll be much more browser friendly and that you can
I think you're on your own with that. So you have to decouple your original source code beforehand and then compile it into different modules through the compiler. Not pretty sure that's how it works. Because the dev tools are not really that developed yet. So the developer experience is not great. And you have to do a lot of things manually, like compiling your original app into different modules. But I think we're getting there. Any other questions? OK. If you think of anything later, I'll be around today and tomorrow probably. So we can just chat about it. It may be more relaxed atmosphere where you're not on the spot. So I guess that's it for today. You can just chill until the next talk.